In this section, we are going to explore the relationship between work and kinetic energy, and also define and arrive at an expression for measuring and calculating kinetic energy. So let's consider a situation where there is a block of mass m on the ground, and there is this person that is going to apply a force in order to push this block. So if you draw the free body diagram of the block, there is gravity acting vertically downwards, the surface pushing it up, which is what we call as the normal force. Since the block doesn't experience an acceleration vertically, these two forces are equal to one another. There is this applied force and there is friction, and let's say the applied force is more than friction, causing an acceleration to the right because there is a net force to the right. So since the block experiences an acceleration to the right, this is going to get displaced to the right, and let's say in a time interval t, the displacement is going to be s. So it started from rest with a velocity of 0, and at the end of a displacement s, it is going to have some final velocity, which is denoted here by v. So we want to calculate how much work the net force does on the object. So the net work done can be written as the net force times the displacement times the cosine of the angle between the net force and displacement. And if you notice the net force is to the right and displacement is also to the right, so therefore cosine of 0. So that makes it F net times S. Let's expand net force. Net force is nothing but a product of mass times acceleration, so it is m times a times s. And we want to rewrite this a, so we can use the equation of motion, which we know the initial velocity and the final velocity and the displacement. So we know that v squared is equal to u squared plus 2as. And since our initial velocity is 0, we can say v squared divided by 2s is equal to a. So substituting, we get net work done equals m times v squared over 2s times s, and the s cancels out, leaving us with m v squared over 2. So the net work done is equal to m times v squared divided by 2, and this quantity is what we call as the kinetic energy of an object. Since the block started at rest, it initially did not have any kinetic energy. So at this position there is no kinetic energy, and at this position it has some kinetic energy. So where did the kinetic energy come from? So we can say that the net work done on the object has resulted in the change in kinetic energy of the object. So your net work done is equal to the change in kinetic energy. If the initial velocity was not 0, then you would rewrite the net work done as simply the final kinetic energy minus the initial kinetic energy. This is v and this is u. So net work done is always equal to the change in kinetic energy. And so this quantity, that is mass times velocity squared divided by 2, is what we associate as the energy of any object in motion. So therefore, a moving object is going to possess a certain amount of energy that is defined by the product of its mass times the velocity squared divided by 2. And that is what we call as the kinetic energy. If you substitute the unit of mass times the unit of velocity squared, which is meters per second the whole square, this comes out to be kilogram times meters per second squared, which is what we know as a joule. So just like any other form of energy, kinetic energy is measured in joule. And notice, since mass is always going to be positive and the square of any number is always going to be positive, kinetic energy is always going to be positive. So how does this work change in kinetic energy theorem allow us to understand the situations? So if your net work done is positive, this implies that your change in kinetic energy is positive. That means there is an increase in kinetic energy. If your net work done is negative, then this implies that your change in kinetic energy is negative. That can be easily understood by looking at some situations. So if you have an object where your applied force is more than friction, we know that, and if it's moving this way, then we know that the applied force does positive work and friction does negative work. So the net work is positive, and therefore there is an increase in kinetic energy. But if you look at it from the force perspective, you know that there is a net force in the direction of motion, so therefore there is a positive acceleration and therefore a gain in speed. If you take a situation where there is no applied force, there is just friction slowing down an object, then the net force is going to be negative and acceleration is negative, so therefore velocity decreases, or in other words we can say work net is negative because it's trying to move this way, displacement is this way, and your kinetic friction is the opposite. So your net work done is negative, and therefore delta KE is also negative. And that means that there's a special situation when your net work done is 0. That means your applied force, as much positive work that it is doing, an opposing force is doing an equal amount of negative work such that the net work is 0. What does this mean? That means there is no change in kinetic energy of the system, or the velocity of the system should stay constant. This we can also understand that if the net work done is 0, that means your net force is 0, which means that your acceleration is 0, which also implies that your velocity should stay constant. So now that you know the relationship between work and kinetic energy, we can understand that there are two approaches to problem solving. You can either find the net force and therefore use it to find the acceleration, and then use kinematics to solve for final velocity or displacement or anything else. Or you could use the net work equals change in kinetic energy approach to determine the final velocity or the displacement. So either of these approaches will work.